Hey everyone, and welcome back to This Explainer brought to you by Forge College. In our last session together, Putting It Together, Mining's Role in Bitcoin's Economy, we mapped out the fascinating economics of mining. We looked at how miners are constantly balancing capital, energy, and expected revenue just to capture those block rewards. But, economics is really just math on a page until you actually plug something into the wall, right? So today, we're transitioning away from the economic theory and moving straight onto the cold, hard, intensely loud physical hardware that actually does all the heavy lifting. Okay, let's dive into this. What physical machines are actually securing the Bitcoin network? I mean, we know that mining fundamentally requires converting raw energy and capital into cryptographic work. But how does that actually happen in the real world? Are these massive mining farms just using the same standard laptops we use to browse the web or check our emails? Or is there something much, much more specialized going on inside those massive data centers? Well, to truly grasp how raw energy transforms into digital security, we need a clear map of the hardware landscape. So, here's our blueprint of the factory floor for today's explainer. 1. Welcome to the factory. 2. CPUs and GPUs, the generalists. 3. ASICs, the specialists. 4. Calculating the trade-offs. 5. The environmental footprint. And 6. Closing the factory. All right, let's jump right into section 1, Welcome to the Factory, specifically the factory model. To really picture this, I want you to imagine every single mining device out there as a production line on this massive, sprawling factory floor. You're hashing throughput, which is just the number of cryptographic guesses a machine makes every second, is basically the speed of our assembly line. And the power draw, measured in watts, is simply how much electricity this massive machinery is just gulping down from the grid to keep the belt moving. Now, this brings us to an absolutely crucial concept for any factory manager out there: efficiency. Simply put, efficiency is the ratio of useful output, so valid hashes per unit of energy. We usually measure this in joules per hash. Think of it kind of like gas mileage for your car. But instead of miles per gallon, we want to know how much raw hashing horsepower we're getting for every single drop of electricity. Honestly, if your factory machinery is chugging down energy but barely spitting out any hashes, well, you're going to be out of business before you even mine a single block.
Moving right along to section 2, CPUs and GPUs. We like to call these the generalists.
Let's start by looking at the older, more general-purpose equipment. First up on the floor is the CPU, the central processing unit. This is literally the exact same hardware most of us have sitting on our desks at home right now. In our factory metaphor, the CPU is basically the administrative workstation. It's absolutely fantastic at handling diverse tasks. It runs your operating system, opens your web browser, and flawlessly juggles 50 background processes all at once. But because it spends so much of its precious silicon real estate on control logic and memory caches just to handle all that variety, it is absolutely terrible at the highly specific, incredibly repetitive SHA-256 assembly line work of Bitcoin mining. It's kind of like asking the factory manager to manually screw in every single bolt. I mean, technically they can do it, but it's wildly, painfully inefficient.
Next up, we have the GPU, or Graphics Processing Unit. Think of this guy as the flexible production line. GPUs were originally designed to render computer graphics, which inherently requires doing a whole bunch of parallel math all at exactly the same time. And it turns out that parallel architecture makes them pretty darn good at certain mining algorithms. But their real superpower? Strategic flexibility. See, if a specific mining operation suddenly becomes unprofitable, you don't just have to throw the machine away. You can easily repurpose or resell a GPU to gamers, video editors, or even AI researchers. They really are the versatile workhorses of the tech world.
All right, section 3, ASICs. These are the specialists, the heavy machinery. Now, what's really interesting about this slide is that this is where the entire Bitcoin mining industry eventually converged. This is the ultimate mining machine, without a doubt the heavyweight champion of the modern network. ASIC stands for Application-Specific Integrated Circuit. This is a hyper-specialized chip designed to do exactly one thing and literally one thing only. In this case, calculate the SHA-256 algorithm. An ASIC completely strips away all of that unneeded generality we saw in a CPU or GPU. There's no control logic for running an operating system here, no graphics renderers, nothing. It is an absolute powerhouse that just packs as many dedicated hash engines into the smallest area possible, operating with basically zero wasted overhead.
And because they are so stripped down and laser-focused, ASICs operate at blistering speeds. We're talking hundreds of terahashes per second. To put that into perspective for you, they deliver orders of magnitude higher hashing throughput per watt than any general-purpose hardware on the planet. Let me paint a picture. If a CPU is someone trying to dig a trench with a teaspoon, and a GPU is someone digging with a solid metal shovel, an ASIC is a massive diesel-guzzling industrial excavator. There is literally no competition. So pulling out our engineer's clipboard here really makes the trade-offs crystal clear. Look closely at the energy efficiency row. The ASIC is the undisputed winner, boasting the lowest joules per hash by a mile. Meanwhile, CPUs have the highest flexibility, sure, but their energy efficiency is the absolute worst. GPUs sit somewhat comfortably in the middle, with moderate efficiency and high flexibility. But here is the hard reality of this business. Because electricity costs are far and away the single biggest operational expense for Bitcoin miners, that dominant energy efficiency of the ASIC, it makes it the only rational choice for any large-scale operation. Which brings us to Section 4, calculating the trade-offs. Specifically, let's look at the short-run margin.
Stepping off the super loud factory floor for a second and walking into the quiet accounting department, we find this crucial blueprint-style math. So, the crucial point is figuring out if a machine is actually profitable to keep running. You follow this short-run margin formula. Step 1, calculate your expected revenue per hour. That's based on your hash rate compared to the total network plus whatever the block reward is. Step 2, subtract your energy cost per hour. That's simply your machine's power draw multiplied by whatever your local electricity price happens to be. Step 3, layer on your CapEx amortization. That just means taking the upfront purchase price of the machine and dividing it over its expected lifespan. If that final bottom line number is positive, great, you keep the machine plugged in. Now, doing this math brings up a hilarious but honestly pretty brutal reality when comparing our machines. The ASIC is a lot like a world-class sprinter with a notoriously short career. It has the lowest operational energy cost for sure, but an incredibly high obsolescence risk. A newer, faster ASIC is inevitably going to come out and make yours entirely useless very quickly, mainly because it literally cannot do anything else. The GPU, on the other hand, is your reliable, steady workhorse. It'll cost you more in energy to mine with it, but it has massive resale flexibility. If it totally fails at mining, hey, it can just go get a job rendering video games.
Okay, moving to Section 5, the environmental footprint. Let's look at the impact beyond just the watts.
Stepping completely outside the factory walls now, we have to look up at the exhaust stacks, because the true environmental impact of all this isn't just your monthly electricity bill. A mining facility's total environmental impact is basically split into two major slices. First, you've got operational electricity consumption. That's the raw power the machines are actively drawing from the grid while they're mining day and night. But the second, and equally important slice, is lifecycle emissions. We also call this embodied emissions. This includes the total carbon footprint from actually manufacturing the raw silicon chips, fabricating the metal casings, shipping these incredibly heavy units across oceans, and then eventually throwing them in a landfill. And here is the real catch, a phenomenon we can call the factory floor Jevons paradox. Because ASICs face such rapid obsolescence, miners are constantly throwing them out to replace them with newer, much more energy-efficient models. Now, upgrading to a more efficient machine lowers the electricity consumed per unit of work, which is awesome. But that high turnover rate creates an absolute mountain of electronic waste. In fact, if efficiency gains lower the marginal cost of mining enough, it might encourage even more machines to be deployed in total. So at the end of the day, a device's lifespan ultimately dictates its true embodied environmental impact. Which brings us to our final section, Section 6, closing the factory. Let's cover our key takeaways. Well, we've seen the machinery, we've done the math, and we've checked the exhaust. So let's quickly recap our core takeaways. Number 1, ASICs completely dominate the network simply because their hyper-specialization provides unbeatable energy efficiency. Number 2, GPUs offer CapEx flexibility, completely cushioning your initial investment risk. Number 3, the rapid obsolescence of specialized hardware is a huge driver of the industry's lifecycle environmental footprint. And number 4, ultimately, the viability of any single operation just comes down to balancing throughput, energy cost, and CapEx. And this brilliantly illustrates how everything ties together. Optimizing joules per hash really is the absolute decisive operational factor for any miner out there. All of this leaves us with one final, pretty provocative puzzle.
Think about it. If ASICs are already hyper-specialized, completely stripped of all extra features, and completely laser-focused on one single algorithm, what architectural choices can engineers possibly tweak next to squeeze out even more hashes per joule? I mean, what is actually left to optimize inside that silicon? Well, you're just going to have to join us for our next explainer on ASIC architecture to find out. Until then, please make sure to visit forge.college to learn more about this subject and to explore all our other deep dives into Web3 topics. Thanks so much for watching and keep building.